Problem 21.12. Consider this quadratic program. Try to minimize this function under the constraint ax less than or equal to b. So now here, q is positive, symmetric and positive definite. A is this. So we guess we need to assume that A is a full rank matrix, but it has more columns than rows. B is a non-negative vector, and the question is to find all the points that satisfy the KKT condition. So it's pretty standard procedure now. Just the Lagrange function. This is gx, and times mu, and then KKT condition is the gradient of L with respect to x. That's this. This should be equal to 0. This is the original constraint. This mu should be greater than or equal to 0, and then this slack completeness condition. And we have that, and then I should say it's called a complementary slackness. It should be equal to, sorry, now we have these 4 equations or 4 conditions right here. We need to solve for x. To solve for this, solve for x and mu. To solve for the x, let's first look at this one. Remember that it's a vector on left and right. Okay, and what I can do is I multiply the x transpose, the row vector, and I will get this equal to the 0, scalar 0. And then also for equation 4, I can see that this, which is this here, is equal to this because I just this is the inner product of the mu and ax. So I can just change their order and let's just keep the value. The value doesn't change. And on the other hand, this should be equal to that. So it's mu transpose b on the right. So that means this is equal to mu transpose b, and that appears here. So if I going to equate that, then it should be replaced by, it can be replaced with mu transpose b. So combining 5 and 6, we'll see that this plus this should be equal to 0. Okay, that's how I got this 7. Okay, now you remember that the x is positive definite, so this one is anyway greater than or equal to 0. On the other hand, the mu is greater than or equal to 0. B is a non-negative vector as said in the question. Okay, so that means the inner product of these 2 non-negative vectors must be greater than or equal to 0. So 2 non-negative numbers add up to 0 means that both of them have to be equal to 0. And if this is equal to 0, but the q is positive definite, so this equal to 0 means that x has to be equal to 0, right? So the x has to be equal to 0, and also this needs to be 0, but it doesn't help us to figure out that x is already known. It has to be equal to 0. And also we can, as I said, can easily check that the x is a regular point, because no matter what its mu is, if we're going to see if it's a regular point, you just find all the mu's, the components of mu that are, I should say, all the active constraints, and form them together, put them together, and take the Jacobian, and that has to be a full rank matrix, because you will get a collection of matrix that extracts certain rows of the matrix A. But A has a full row rank, so all the rows are linearly independent. So if you extract a few rows of A, they have to be linearly independent as well. And that means the Jacobian has to be full rank, and this means that x has to be a regular point. So it's a regular point, and it does satisfy the KKT condition. If x equals to 0, you see everything is okay. And then, you justify that x is actually the only point that satisfies the KKT condition. Okay, now we need to check the second order sufficient condition if it is satisfied. So now remember that the G is this. G contains the G1x, G2x all the way to Gmx. And the Hessian of each one of those should be equal to 0, because each one of them is the alpha function of x. Okay, it's linear in x. I should not say linear, it's an alpha function of x. So you take the Hessian, they will be equal to 0. Okay, and then you take the weighted sum of the Hessians. Every one of this is equal to 0, and this Hessian of f is just 2q, as we said, and it's a positive definite. So it doesn't matter. We don't even need to worry about the t tilde thing, because now for this matrix, for any non-zero vector, you multiply to both sides of q, you get 0. You get a positive number. So it does satisfy the second order sufficient condition. So that is the only point, x equal to 0, and then that satisfies this first order sufficient condition. And that is not surprising, because when you look at the question here, it asks you to minimize this, and apparently this has to be greater than or equal to 0, and is equal to 0 if and only if x is equal to 0. And x equal to 0 satisfies this constraint, because on the left, if x equal to 0, the whole thing is just 0. The b is a non-negative vector, so that means this is always satisfied at x equal to 0. So apparently, x equal to 0 is it's a local minimizer. Okay.